So, welcome everybody. So today's speaker is Andrea Malchiodi from the Scuola Normale Superiore in Pisa, and he will talk about critical points of the Moser-Trudinger functional. Thanks for coming. Take it away.
Okay, thank you very much, and also thanks to all organizers for the kind invitation. All right, so I would like to discuss some joint works, one in progress with Francesca De Marchis from Rome, Olivier Druet and Thizy from Lyon, and Luca Martinazzi from Padua. Okay, so let me begin recalling the Moser-Trudinger inequality. So I start from a smooth bounded domain in R2, and I consider the space W120 of omega. So omega is the domain. So this embeds into all the LP spaces, but not in L infinity. Okay, on the other hand, it was shown by Pojav in 65 and Trudinger in 67 that if U is in W012, then the exponential of e to the U squared is in L1. So you get a sort of limiting embedding of exponential class. So Moser then in 71 proved a sharp inequality. So this is known as the Moser-Trudinger's inequality. So somehow, even though Pojav worked on that before, somehow it was published in the Russian literature. So I only recently found out. Anyway, I refer to this as the Moser-Trudinger inequality. So Moser proved the sharp version. So he proved that if you consider functions whose gradient in L2 is bounded by 4 pi, so that are 0 at the boundary, okay? So you can take the completion of functions supported in omega. So then the supremum of e to the U squared is uniformly bounded by a constant that depends only on omega. The constant is sharp because if you extremize, so if you try to extremize with the supremum within gradient bounded gradient squared bounded by lambda with lambda greater than 4 pi, then the supremum is infinite. Okay, so this is an important inequality in many applications, especially one I'm interested in are Liouville equations, where you consider like minus Alphasan of U equal to exponential of U. And these kind of equations have a prominent role in conformal geometry, mathematical physics, and spectral theory. So here there are some books where you can see the role. Books are by Oben, Dune, and Tarantello, for example. So the first is more geometric. The other two are more, say, mathematical physics directed. And then there are also papers by Osgood, Friedrich, and Sarnak showing the role of Liouville equations in spectral theory. Okay, so if you try to solve then this extremal problem, so you fix the L2 norm of the gradient equal to lambda, so L2 norm squared, so call m lambda this constraint, and try to extremize this functional f of u, which is the integral over omega of e to the u squared. Okay, so then this would be your Euler-Lagrange equation, where lambda comes out as a Lagrange multiplier, essentially. Okay, so you recover just the value of the Lagrange multiplier by basically integrating the equation, multiplying by u and integrating the equation. Okay, so there was a fundamental work by Carlson and Chang in 1986. So they showed that if you are on the unit disk, then the supremum of this functional f is attained in the borderline case, so when capital lambda is equal to 4 pi. So we saw before that the supremum is bounded, and they say that in the unit disk, it is also attained. So they do it using some blow-up analysis, so by sort of a contradiction argument and a test function estimate. Okay, so they show that somehow there is a threshold value, and if you are above this threshold value, then the supremum is attained. So it's a sort of threshold to get compactness. Then Struwe in 1988 proved also some stability result, which is roughly as follows. So for the unit disk, this functional f has a supremum, okay? And so you have a local maximum. So now if you perturb a little either the domain or the value of lambda, then this local maximum geometry persists. And then you're going to find still solutions that are local maxima, even when the supremum is not attained, for even larger values of lambda. Okay, and he proved it via concentration compactness. Then Flucher proved that the supremum is attained for general domains. And he used somehow trig inequalities. So the isoperimetric inequality, Boltz's inequality, and the notion of conformal radius and Robin function. So the question I'm interested in is how far can you go beyond 4 pi to find constrained critical points? Okay, so we saw that the threshold lambda equal to 4 pi is sharp. So if lambda is bigger than 4 pi, we saw that the supremum of this energy is infinite, okay? But still, you may want to find constrained critical points of saddle type. Okay, so let's see some examples, okay? So let me discuss first the case of the disk. So I consider the radial case and the case of the ball. So for the ball, with Martinazzi some years ago, we showed that there exists some number lambda sharp greater than 4 pi, such that the constraint functional has in fact no critical points if you are beyond lambda sharp, at least 2 critical points if lambda is between 4 pi and lambda sharp, and at least 1 critical point for lambda between 0 and 4 pi and lambda sharp. Okay, so the possible scenarios are the following. Okay, so for the ball, if we are, say, less or equal than 4 pi, there is always a supremum. Okay, by Struwe's result, we can go a little beyond. And we showed that's this scenario, essentially. So there is like a threshold value, lambda sharp, beyond which you have no more solutions in the unit disk. Okay, but there is this fact, say, what is this? I'm sorry, I don't know what I've done. Sorry. Okay. On the other hand, so this was the situation for the ball, but if you take annuli, okay, so then the constraint functional has critical points for all value of lambda, okay, no matter how lambda is big. Okay, so let me discuss somehow basically the geometry of this constrained functional. Okay, so when lambda is close to 4 pi by Struwe's results, the local maximum persists. But if lambda is bigger, then the supremum is not attained. Okay, in fact, the energy is unbounded from above. Okay, so the picture is like this. And this suggests that there might be, in fact, a second stationary point here, like a saddle point. So we are tempted to use a sort of reversed mountain pass scheme. So for the mountain pass scheme, you usually start from a local minimum, And then you require the existence of one point for which the energy is very negative, and then you're going to find like a saddle point here. And this is like a reversed situation, okay? In fact, so this was done by Struwe and Robert Struwe. So they proved the following. So for any domain omega in R2, there exists some epsilon such that if lambda is slightly above 4 pi, then indeed the constraint functional has at least 2 critical points. Okay, so we can make this picture into a real theorem. Let me discuss other example. Okay, so when so somehow this local maximum persists when lambda stays close to 4 pi, okay, by roughly a perturbation argument. But when lambda is much larger, then there's no more reason to believe in the existence of this local maximum. Okay, so the geometry of the function could be completely different. Okay, and another family of solutions was constructed for lambda slightly bigger than not 4 pi but 8 pi. Okay, so twice the threshold value for the existence of an upper bound. So this was proved by Del Pino, Musso, and Roof. So it's like a constructive proof using refined implicit function arguments. So they show that whenever you have a domain which is non-simply connected, so you need a hole, then you can find the small epsilon such that for lambda in this range, so if you are between 8 pi and 8 pi plus epsilon, then you have at least one critical point of a two-peak type. Okay, so they construct solutions that concentrate as epsilon goes to 0 to a function which is a superposition of like two spikes. And they also found similar solutions with k peaks in round annuli. So they would be distributed on the vertices of regular polygons with some extra symmetry. Okay, so these results suggest somehow that the topology of the domain should play a role in the existence of constrained critical points, because we saw that on the disk, if you take lambda too large, then there are no more solutions. But on annuli, then you can find solutions for large values of the constraint lambda, okay, of the Dirichlet energy. Okay, in fact, more in general, we will see that there are ways to use improved versions of the Moser-Trudinger inequality, and they do exploit the topology of domains. Okay, so in fact, sometimes this best constant for pi can be improved. And let me discuss some well-known example somehow for the weaker Moser-Trudinger inequality, so involving not quadratic growth, but linear exponential, say. Okay, so Moser proved in 1973 that a version of the Moser-Trudinger inequality improves for functions defined on S2 that are antipodally symmetric. Then Oben improved this result. So he proved that there exists an improved version of the Moser-Trudinger inequality for functions whose exponential have as center of mass the origin of R3. Okay, so we have S2 sitting in the three-dimensional Euclidean space. You take e to the u as a measure which is defined on the sphere. Okay, and then you can compute the center of mass of this measure. So if the center of mass is at the origin of R3, so somehow if this measure e to the u is uniformly spread over the surface, then you can improve the Moser-Trudinger inequality. So the nice aspect of Oben's result compared to Moser is that somehow Moser's result requires antipolar symmetry, which is like an infinite dimensional constraint. But Oben's condition is a finite dimensional constraint. Okay, so it's typically a condition that holds for a set of codimension 3 in your space W12 of the sphere. Okay, So it's a finite dimensional constraint, and usually it's some condition that you can catch if you apply, for example, Möbius maps. So Möbius maps are conformal maps of the sphere that might carry around the volume from, for example, the North Pole to the South Pole. Okay, and if you start with a volume distribution, and if you apply a suitable Möbius transformation, then you are always able to set the center of mass at the origin of a tree by essentially a degree argument. Okay, so it still happens, say, rarely, but not as rarely as for Moser's result. Okay, so typically it's a condition that you can catch via some kind of transversality argument. And we will see a sort of a simplified version of this in the next slides. Okay, so what is the basic principle beneath this inequality? Okay, so let me state a general improved inequality, okay, which holds in this case. Okay, so suppose that you have two subsets, call them S1 and S2, at a positive distance, delta, one from the other, at least delta, okay? And you assume that each of the sets contains a finite portion that I call gamma of the integral of e to the u squared. Okay, so somehow the mass is distributed, so at least a finite portion of the total mass is distributed in each of the sets, and these two sets are separated by a positive distance. Okay, so then what is the conclusion? That for any epsilon, there is a constant such that whenever u satisfies this condition, and whenever the gradient of u squared is bounded by 8 pi minus epsilon, then you get an upper bound on f, okay, on the integral of e to the u squared. So what is the meaning of this proposition? So we saw that this quantity was bounded by the Moser-Trudinger inequality when the integral of radius squared was bounded by 4 pi, okay? Now, if we have this extra condition like a spreading of the mass into separate sets, then here we can reach almost 8 pi. Okay, so we have an improvement somehow of the best Moser-Trudinger constant. So the proof is a bit tricky and uses basically a localization and some Fourier analysis. So very roughly, you multiply u by a cutoff, and then you use the standard Moser-Trudinger inequality on u multiplied by the cutoff. So basically, in this way, you're able to split the Dirichlet energy into two parts, and then you use the best of the two. Okay, so what kind of conclusion can you reach out of this improved inequality? Okay, so if you use a covering argument, you can characterize high energy levels of f if lambda is between 4 pi and 8 pi. Okay, so we saw that when lambda is greater than 4 pi, you lose upper bounds on the energy. But here, if lambda is between 4 pi and 8 pi, okay, you may lose upper bounds, but you can somehow derive some information on the functions for which you lose upper bounds. So you reason as follows. So we saw that a spreading of the mass gives you a better constant in the Moser-Trudinger inequality. And once you have a better constant in the Moser-Trudinger inequality, then that favors upper bounds on the energy. Okay, so if you have this spreading condition, then you still get the upper bounds on the energy. Now, what happens if the upper bounds fail? Okay, so if the upper bounds fail, it means that you don't have a better constant in the Moser-Trudinger inequality, which means that the mass cannot spread quantitatively as we saw before. Okay, so the consequence is the following. If the mass is not spreading, it means that it must concentrate at a single point. Okay, so we have somehow the following behavior Okay, so you fix lambda between the first threshold and the double, so between 4 pi and 8 pi. Okay, then for any epsilon and r, there exists a large number L, so that if you are on the constraint, so with the Dirichlet energy equal to lambda, and if the energy is large enough, then somehow almost all the mass is concentrating near a single point. Okay, so only an epsilon fraction of the total mass lies outside a small ball around this point. Okay, so it means that okay, you lose upper bounds, but if the energy gets very large, all the volume, so all the mass is concentrating near a single point. Okay, and now you can exploit the topology of domain that is not simply connected. Okay, suppose the domain is an annulus, for example, and that lambda is within this range. Okay, so let me recall the definition of the constraint. So Dirichlet energy, sorry, here there should be a square that I missed, is equal to lambda. Okay, so then you can find a so-called barycentric map, okay, which is continuous. So this sends somehow high energy levels into the domain itself. Basically, we saw that when the energy is very large, all the mass is concentrated near a single point. Okay, so this map, which I call a barycentric map, psi, it's like a projection. So it's sending functions with high energy to the center of mass of the function e to the u squared. Okay, so we saw by the previous proposition that it must be concentrated near a single point. Okay, so I'm just mapping a function into the center of that ball containing almost all the mass. Okay, I call this map psi. Okay, the point is that now if the annulus encircles the origin, we can get a condition similar to Aubin's. So to Aubin's center of mass. So let me try to explain. Okay, so when the center of mass of the volume distribution e to the u squared, so if the center of mass of that is at the origin of R2, okay, and I'm assuming that the origin lies in one of the holes of the domain, then there's no chance for the mass to be concentrated at a single point. Okay, because if it is concentrated at a single point, then the center of mass will lie in the domain. But I'm assuming that the center of mass lies at the origin of R2, so outside of the domain. So it means that there must be at least some spreading of the volume. Okay, so this is very similar to Aubin's, but we can do also a vice versa. So I can construct a sort of opposite map. So I can map the domain into arbitrarily large levels of the energy via some construction of test functions. Okay, so let me take lambda in this range, 4 pi, 8 pi, and let me consider a non-contractible circle that I call C in omega. So then for any point of C, there exists some test function phi lambda x in the constraint, such that the energy goes to plus infinity, and such that the mass distribution is resembling a Dirac delta at the point that you chose. Okay, so this is what is happening. So I consider domain omega with a hole, say, containing the origin. And now I draw a non-contractible circle C inside the domain. Well, then for any point in the circle, I can find the test function whose mass is concentrating at the given point and whose energy is going to plus infinity. Okay, now this map somehow goes well with the one we constructed before, okay, because what did we do before? So there was this map psi. So this map psi was mapping functions with very high energy into the center of mass. Okay, so it associates to a function with large energy a point in the domain. Okay, while these test functions were doing the opposite. Okay, so we were starting from a given point in the domain, in particular on this circle, and we were finding functions that were concentrating there with very large energy. Okay, but we can go basically from one set to another, so from the domain into functions with large energy, and then via the barycentric map back to the domain. And if I do this, I obtain a map which is approaching the identity. Okay, so I start from a point in X in the circle C. Then to that, I associate this test function, which is concentrating here. And then I associate to this function its center of mass, which will be close to the initial point X. Okay. So when I send lambda to infinity, so when this function becomes more and more concentrated, the composition of the two maps, so first I associate to X this test function, and then the barycentric map. So when lambda goes to infinity, this map converges to the identity on the circle. Okay, so now we can do some min-max scheme, which is inspired by some work also by Guofang, okay, from 1999. Okay, so let me consider topological disk in R2, whose boundary is this given curve. Okay, so this disk is contained in the whole of the domain. And then I do the following. So I consider a map theta from the disk that I call D into the constraint. So M lambda are the functions with Dirichlet norm equal to lambda, such that at the boundary, this map coincides with this spike functions constructed before. Okay, so now we know the following, that so this map is defined from the disk into my functional space, and it's very large on the boundary, okay, because the energy when I send lambda to infinity, then F is very large. So at the boundary of the disk, this map is very large. But I know by degree theory that somewhere inside the disk, the center of mass must be 0. But when the center of mass is 0, then I get an upper bound on the energy. Okay, so this situation is like of the one of like a minimum. Okay, so it is possible to run a reversed two-dimensional min-max scheme. Okay, using two-dimensional disks to find something which, in principle, could be a critical point. Okay, so we have somehow enough topology to run non-trivial min-max schemes. Okay, so this was somehow a particular case. So let me present the theorem. Okay, so jointly with the Marchis, Martinazzi, and Thizy. Okay, so let me consider a closed surface instead of a domain, and a number lambda positive, any number. Then this, so for any choice of lambda, the functional f has a constrained critical point to this manifold m tilde lambda. Okay, so the functions in W12 whose W12 norm is equal to lambda. Okay, so I recall that for lambda greater than 4 pi, then it is not possible to maximize this energy, but still we can find constrained critical points. Okay, so I gave a sort of outline of the idea in a simple case. So when the domain was not a surface, but say a planar domain with holes with some topology, and when lambda was between 4 pi and 8 pi, okay, the case of general lambda uses a more involved min-max scheme. Instead of allowing concentration at a single point as before, if lambda is bigger, then you might allow concentration at a larger number of points, but still upper bounded. Okay, so this is inspired by some min-max scheme which I developed with Zindin Jadli to deal with the Liouville equations, essentially. Okay, and we also have related results for domains over 2, which I will state later. Okay, so far I sort of presented the geometry of the functional, but I kind of cheated a bit on you in the sense that whenever you run some min-max scheme, to be sure that you obtain critical points, you need some kind of compactness conditions, okay? Because if you run a min-max scheme, what you will get in general is a Pallas-Mail sequence, which is a sequence of approximate critical points. So you want to make sure that these approximate solutions somehow are related to true solutions. And for this critical functional, this is really an issue. Okay. So as I said, if you run min-max schemes, well, you get only Pallas-Mail sequences. Okay. It's like saying, okay, if you have a functional bounded from below, it's not guaranteed that there is a minimizer, because you might have a function with an asymptote, so a function behaving like 1 over x in R, for example, and any minimizing sequence there would diverge. Okay, so if you try to use to minimize this energy, you don't get a minimizer, but you get a Pallas-Mail sequence. So a sequence of points for which the gradient is more and more flat somehow. Okay, but they do not converge. And it's kind of a similar situation here. Okay, so what is known about the Pallas-Mail condition? Okay, not so many good news. So it's known to hold when lambda is less than 4 pi, so when you can actually maximize the energy. And that was proved by Adimurti and Struwe. But it actually fails when lambda is greater than 4 pi. Okay, so this was shown by Costa and Tintarev. So not only you cannot maximize the functional, but even the Pallas-Mail condition does not hold. So, I mean, even if you run these non-trivial min-max schemes, then you're not guaranteed to converge to a solution. Okay, but there is a sort of meta principle. Okay, so Pallas-Mail sequences are approximate solutions to a given equation, okay? But it's better to do the following. So it's better to perturb the equation and to find exact solutions of a perturbed equation rather than dealing with approximate solutions of a given equation. Because somehow when you solve exactly one equation, then you might get, in fact, a lot more information. Okay, so in fact, say the Pallas-Mail sequences here are actually very wild. Okay, so if you're used to somehow concentration compactness in geometric analysis, there is a typical behavior that you would expect, like the existence of a weak limit plus some given number of bubbling points. Well, here, I mean, these Pallas-Mail sequences are very wild, so, and they're not converging. Okay, so we instead try to perturb the equation and to find exact solutions, okay? So since the nonlinearity e to the u squared is somehow critical for the Moser-Trudinger embedding, well, anything that grows slower than that would have also some compactness properties by basically the Danforth-Petit results, okay? So if you take an exponent p less than 2, then, okay, we try to solve for this equation, which corresponds to our original equation for p equal to 2. But now p is lower than 2. Okay? And we still lay on the constraint with of functions with Dirichlet energy or W12 energy equal to lambda. W12 energy squared. Okay, so the idea would be to try to pass the limits for p converging to 2. Okay, so let me discuss this approximate equation. Okay, in fact, okay, still bad news. Even for this, say, equation with a milder nonlinearity, it is not known whether the Pallas-Mail condition holds or not. Okay. What is standard, so which is given you by somehow the compactness of embedding into functions of this form, of W12 into functions of this form, is that if Pallas-Mail sequences are bounded in W12, then you converge to a solution of the problem. So the Pallas-Mail condition holds for bounded Pallas-Mail sequences, but not in general. Okay, and if we run this min-max scheme, we don't know the boundedness of these Pallas-Mail sequences. So we get some Pallas-Mail sequence, but we don't know whether it's bounded in norm or not. Okay, so there is a way out of this. So there is a by now classical argument by Struwe, which is called the sort of entropy method. Okay, so you introduce some sort of extra parameter in the problem for which you have some kind of monotonicity property. You can think of a sort of viscosity term, okay? And then you can derive existence for not all values of this parameter in the perturbation, but for almost all values, okay? So this is a method that has been used successfully in the study of minimal or constant mean curvature surfaces, harmonic maps, and also Liouville equations. Okay, so it was used, for example, in the paper by Ding, Yost, Li, and Wang that I mentioned before. Okay, so then we came up with a sort of approximation of the function f, which is the following. So, sorry, it's a bit involved to write it down. Okay, but so lambda is the constraint on which we're working on. Okay, so we work with functions in whose W12 norm squared is equal to lambda. And then for p less than 2, we consider this function. Okay, so then what we can do is that, okay, we cannot find critical points of this directly, but we use lambda as a parameter. Okay, so we give up our original constraint. And using this monotonicity trick by Struwe, so since this energy depends monotonically on lambda, so we can think of lambda as a sort of entropy, like a viscosity, okay? For almost all values of lambda, we can find actually a critical point, okay? Because if p is less than 2, then we have some compactness properties, okay? And somehow the monotonicity with respect to lambda gives bounded Pallas-Mail sequences. Okay, so we're able, using the previous min-max scheme, to find critical points for almost all values of lambda. Okay. By the way, at what time am I supposed to stop?
45. You have like 7 minutes.
Oh, 45. Oh, okay. Then I should speed up. Okay. Okay, so then the next goal is to check whether the sequence converges or not. Okay, so when we send p to 2, do we get convergence? Okay, and okay, so something that you can see is that there is a formation of bubbles. Okay, so you can somehow rescale properly your solutions to find a sort of limit problem. So here the scaling is a bit tricky. So it was done by Struwe the first time in 1988, okay? So UKs, so the UKs are functions that are blowing up, okay? And if you define these new functions, eta k, then they satisfy an approximate Liouville equation. So Liouville equation is of the form Laplacian equal to the exponential on the right-hand side. And such solutions were classified, okay? And these solutions were classified by Chen and Li as bubbles. So they are related to conformal factors of the stereographic projection of S2 in R2. Okay, so what you can prove is that on small scales, when you do this change of variables, you have a good control on the solutions and on the Dirichlet energy. Okay. So the question is, what about larger scales? Okay, so there was a quantization result proved by Druet on domains over 2 and Young in on compact surfaces. Okay, so if you consider a sequence of solutions UK to this equation with P equal to 2, uniformly bounded in energy. Okay. So then there is a splitting of the Dirichlet energy into the Dirichlet energy of some weak limits, u infinity, and basically a finite number of bubbles as before. Okay, there is also a related parabolic version by Lamma, Roberto, and Struwe, using not exactly solutions, but solutions of a parabolic flow. Okay, and with some hard analysis, Druet and Thizy proved that indeed the weak limit has to be 0. Okay, in which case you get a full quantization. So if there is blow up, then the Dirichlet energy converges to a multiple of 4 pi. And this is more similar to what one usually sees in geometric analysis somehow. This result was proved previously by Martinazzi and myself in the radial case, but then with a much harder analysis, it was extended by Druet and Thizy. Okay, the consequence is that you have compactness whenever the value lambda for the constraint on the Dirichlet energy is not a multiple of 4 pi, okay? Because in that case, so since this is equal to lambda, then it cannot converge to a multiple of 4 pi, okay? So in this case, we do have compactness. Okay, and in this work, we extended this analysis to all exponents p between 1 and 2. So this was only done for p equal to 2. Okay, so what do you do when lambda is a multiple of 4 pi? Okay, so thanks to the previous estimates, we proved the theorem when lambda is not a multiple of 4 pi. Okay, and in general, you do expect a blow up of solutions when lambda converges to multiples of 4 pi. Because we saw it in the example by Del Pino, Musso, and Ruth. So I recall that they considered annular domains and they constructed multi-peak solutions whose Dirichlet energy was exactly converging to multiples of 4 pi. However, there is some work which gives you a hint, so by Mancini and Martinazzi. So they showed that for lambda converging to 4 pi, blow up only happens from the right-hand side. Okay, so in this paper, I recall that lambda was slightly beyond 8 pi. So lambda was between 8 pi and 8 pi plus epsilon. Okay, so what Mancini and Martinazzi proved in the radial case is that, okay, if this is the picture of solutions, as described in my paper with Martinazzi, well, then you can only have blow up from the right-hand side, okay? And we were able to prove this also in the non-radial setting, okay? And for all p's between 1 and 2 with 1 excluded, okay? And let me remark that this property is actually false when p is equal to 1. Okay, so somehow Zhang and Lin in some papers from 2002 and 2003, they determined somehow the sharp conditions from which you can have blow up on the left or on the right. Okay, so to conclude the proof, now, okay, we take a sequence. So we assume that lambda is a multiple of 4 pi. And now we take a sequence of lambda k's which converge to this multiple of 4 pi from the left. Okay, and then by the previous results, then solutions must be uniformly bounded and we have existence. Okay, so the global picture of solutions is something like this, more or less. Okay, maybe I skip the next theorem and I pass to discussing some open problems, okay? So in the radial case, this is more or less the conjectured picture. So there is some lambda sharp beyond which you have non-existence, and then you might have blow up from the right at 4 pi, okay? So it would be interesting to prove uniqueness or exact multiplicity results for the disk, okay? Or to see whether one could extend this non-existence result for lambda large, also for, say, more general convex sets, for example, or maybe contractible domains. It would be also interesting to prove multiplicity results, because somehow we saw that the topology is very rich, and whenever the topology is rich, then it's a sign of the existence of multiple solutions. Okay, so Francesca De Marchis proved some generic multiplicity results, but that was for the Liouville equation, so it would be nice to prove them also for this equation, maybe even remove the genericity. Okay. The other question is, are there maybe natural conditions under which you might recover the Pallas-Mail condition? Okay, so for example, if you assume like a Morse index bounds on your Pallas-Mail sequence, so there is a notion of Morse index even for not exact solution but approximate solutions. So maybe under this condition, can you recover the Pallas-Mail condition? Also, the case of changing sign solutions is very challenging. Okay, and in a recent paper, Martinazzi, Thizy, and Betoit show that somehow the blow-up behavior can be completely different. So in this case, you might get non-zero weak limits differently from what we saw before. And somehow the interaction of bubbles with different signs can completely change the picture. Okay, so maybe I stop here and thank you for the attention.
Thank you very much.